So I will start. I will start in 2-3 minutes mostly. I request kindly set a revision session next week. Just one more hour as per future. See, that is not up to me. Like I know there used to be revision classes previously, but this is the last session today. I don't know whether there is a revision session this week, has been planned by NPTEL or not. If like previously, I know that the revision classes used to be taken by the professors. So I don't know what is the plan this time. Mm, like if you have any doubts, you can ask me today. Like I will help it out. Okay, so let's start. Yeah, the link will be available. I know that link has been generated by me. Um, okay, what I can what like if it is required, like I don't know whether this like I will be there present next week at this time, but since the link is there, so what you can do is you know my email ID, right? If you know my email ID, okay. So this is my email ID. So this is my email ID. So what you can do is just give me a I'm not sure like Tuesday I will be available at 6 or not, but uh, like if you just remind me that day once, like through a mail, mm, and I will set up a time. Yeah, yeah, like that I will do. Like just mail me once that if you have any required doubts regarding it, I will help. Okay, so let's start today's session. So hello everyone, my name is Rajoy Mukherjee, and this is the problem solving session for the week 12 for NPTEL course on computer organization architecture. So will be solving some problems regarding this week 12 like syllabus that is part of, like the questions will be part of the assignments and similar to ones in the assignment or uh, the end exam. So um, feel free to ask any question while we are doing it. So let's begin. So this is the first question. In MIPS 32 floating point extension, for double precision operation, the register pair F14, F15 will be referred as F15, F14, F13, F12. Okay, so uh, if you have gone through the lecture, you know, for double precision operations, 64-bit register pairs are required. Now, see, in MIPS 32, the name says that the registers are 32-bit, right? So how are we going to store these 64-bit operations? So we need like 64-bit registers, but they are not available. So basically, what we do is we take two corresponding registers, suppose R0 and R1, each 32-bit, for this purpose, for storing the for these double precision operations. So like if we are using registers pair F14 and F15, this will be the it will be referred as F14, the one with the first. So in this problem, it is asked like if the register pair F14 will be referred to as F14. So now what will be F15? F15, if we use, it will be basically the register pair F15, F16, like that. So the correct answer will be in this case B. I mean, this is a very basic question, but like I saw this kind of questions are asked in assignment, so like it is useful to practice this. So if you have any doubt, you can ask regarding this. It is basically very basic. So always, if we use a register pair, so if suppose the question is reversed, suppose it is given that what does F14 refer to? So in that case, it will be, it refers to the register pair F14, F15. I mean, that vice versa question can be asked. So like that is how it is named. The nomenclature is like that. So let's go to the next question. Oh, once again, okay, sure. So basically, double precision operations require, like if you are familiar with double precision operations, so basically they require 64-bit register pairs, registers. So, but in MIPS32, all the registers are 32-bit, right? So how can you you require 64-bit, but you have only 32-bit registers. So what is like the like any architecture designer will think, okay, so let's use two register pairs, two registers. So that's why the architecture is basically have two registers of 32-bit each. So here it is asked like what does how will we refer F14 F15? F14 and F15 together will be one register pair. That will be referred to as always F14. So similarly, like suppose you are given that what does F16 refer to for a double precision operation in MIPS32 floating point extension. So what you will do? F16 will refer to F16 and F17 register pairs. It's simple. Okay, so let's go to the next question. So consider the floating point instruction, load F2, R400, R6. The data location R6, the data location R6 plus 400 and R6 plus 404 will be loaded to which of the following registers? So basically, this is a LD is a load operation. So what does this statement means? LD F2 400 R6. So it is said it is a floating point instruction. Now we know floating point instructions are basically 64 bit, but this is a MIPS 32. So as I said, like, so basically this will be actually a 64 bit memory chunk. So suppose this is 400 and this is 404. So this is 32, this is 32. Now so it is been loaded to register F2. So this part will be loaded to register F2. Now we have seen the nomenclature in the previous problem. What does nomenclature F2 means in this floating point operations? In this floating point operations, nomenclature F2 means, because these are register pairs, it simply means F2, F3. So this chunk starting at address 404 will be mapped to F3. Right, so the correct answer is B. Any doubts regarding this? This is simply the opposite of what was there in the previous questions. Like previous question, it was given what does F14, F15 means, and this question it is given like what does F2 means. F2 stands for F2, F3, and the memory chunk, that is the 64 bit, will be divided into two locations. One will go to F2, another will go to F3. Okay, so let's go to the next question. Okay. So which of the following techniques can be used to improve CPI? Sequencing unrelated instructions, separating related instructions, loop unloading, or D, none of the above. So if like in previous week we have shown, like we have also like studied that CPI, cycles per instructions, get affected is affected by data hazards. And control hazards. Right. So how can you what is the direct effect of data hazards or control hazards? Stalling in the pipeline. So how to improve this, CPI? Like what are the steps can we use to improve the CPI? That is a big problem. Like how to improve the CPI? As we have seen, like there are many steps in which CPI can be improved. One of the main like way to do it is reordering of the code. What happens in reordering in the code is related, there are some codes, like there are some statements which can be executed without interference of, suppose you have a load instruction, load on R1, suppose R2 500 reductor, right? And another you have a suppose add instruction R3 R1 hash 8. So obviously this has a like read after write hazard. Suppose there is another statement. Suppose you see you have a sub statement with R4 R6 okay. So now you see this doesn't have any data hazards, like any data or like dependency on any of these two instructions. So what we can do is, after executing this code, like let me just use a different color. So what we can do is, after executing this code, we can execute this code, and after that, so 1 2 and 3, then execute this code. So that will remove the hazard data dependency, one of the data dependency on R1, that can be removed by this simple reordering of the code. So this is one of the possible way to prevent improve the CPI. Another way is like this is a very common way. Another way which happens only in case of looping is loop unrolling. What happens in loop unrolling is that, suppose you have a looping statement. So what happens, suppose you have a very simple looping statement of for I is equal to 0, I less than 10, I plus plus, I equals to I plus 1. Suppose we have this. So what happens is, it just unrolls one time or two time depending upon the requirement. So that also has been found to reduce CPI considerably. I will show it with an example in the later part of this session, like how loop unrolling helps in improving the CPI. So that is one of the way of improving the CPI. So like in this question, all A, B and C are correct, because all of them help in improving the CPI. So if you have any doubt regarding this, you can ask. Okay, so let's go to the next question. So which of the following statement is or true for superscalar MIP32 MIP32 machine? It can issue multiple independent instruction at every clock. It can result in a CPI less than 1. It can dynamically check dependencies between instructions. It consists of more than one functional unit that can run in parallel. So like if superscalar, what does a superscalar machine does? A superscalar machine basically identifies the dependency between the instructions and issue like it checks the dependency between the instruction and issue multiple independent instruction into multiple functional unit at the single time, which results in less than in CPI less than CPI less than 1. So what happens is like in a superscalar, '32 machine, the checking of, so this happens in order, you can say this, like this happens one after the another. So checking of dependencies, and once the dependency is checked, it issues instructions which can run in parallel. And how it can run in parallel? Because there are multiple functional units, so that's why it can run parallel. And the effect, CPI becomes less than 1. So this is the complete, you can say, a gist of how superscalar MIPS32 machine works. So what it does, it first checks like when a list of programs, like okay, program like a process is always in running, so it always checks whether there is a dependency over a set of statement or not. If like after checking the dependency, okay, this set of instructions can run parallelly, so it issues all of them together, issues them in parallel. Because, and why it can run in parallel, because previously if you have like watched the previous week's lectures, you have seen that there is only one of the main issues was there was only one instruction fetch unit, only one decode unit, only one execution unit, only one write back unit. So those are one. But here there are multiple such units. There are multiple such functional units. So always the non-dependable instructions can run in parallel. And as a result, since more than one instructions are running simultaneously, the CPI will become less than 1. Ideally, CPI is 1 means one, like each instruction is executed per unit time. One unit is like one instruction is executed per unit time. But since multiple instructions are now getting executed, so the CPI becomes less than 1. So if you look at this question, like all of them are true. All are true. So the correct answer is E. None of these are false. Okay, so if you have any doubt regarding this, you can ask. Yeah, sure. So what happens in a superscalar MIPS32 machine? So what happens is, so there is this concept called out of order executions. So multiple instructions can run parallelly. So if you have noticed in previous class, in previous like week, you have seen that there is only one pipeline. In the pipeline, there is only one instruction fetch, only one instruction decode, and only one execute. So all these units were one, 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 one. Now if you know like this is not always the case. So suppose if you have a multiplication instruction, that it will obviously take more time than a simple addition instruction, right? So it is not like sufficient that we always assume that this execution unit will always give instruction, like execute only in one cycle. That it is not always correct. So also that there are dependencies. We have already seen that the concept of hazard, where multiple like due to dependency hazards occur. So what happens in MIPS 32 unit? So in MIPS 32 machine, superscalar machine, there are more than one functional unit. Functional unit in the sense instruction fed, decode, execute, write back. These all functional units are available in abundance. So what it does, it checks a section of code and observe whether that like it finds out like what are the dependencies present in those set of equations. So after that, what it does, it sorts it into a group, like into groups like which can run in parallel. So and executes them in parallel. So when like in previous examples, like previous week's example, what I have seen that each instruction is getting executed in one cycle. So ideally CPI was 1 in case of normal execution. Now since we are executing all of them parallelly and there are multiple such pipeline loops because there are multiple such functional units, so CPI becomes less than 1. So that is one of the beneficiary of this superscalar 32 machine. So if you in this question, like all of the statements given are true, that it can issue multiple independent instruction every clock cycle, it can result in CPI less than 1, it can dynamically check dependency between instruction, it consists of more than one function unit that can run in parallel. Okay, so let's get to the next question. For every instructions, because they are happening more than one in one group. Yeah, that is one of the there are more than one functional units. Like the entire pipeline, there are not only one single pipeline. There are more than one such pipelines available. So that's the reason CPI can becomes less than 1. Yeah, true. Since parallelism is at its peak, so that's why CPI becomes less than 1. Now we will discuss loop unrolling in a little detail. So loop unrolling requires significantly greater number of registers. Yes, it requires more than like there are. It requires more registers than usual. It's true. So now let's discuss this loop unrolling in a detail. So suppose we have this loop for I equals to 1000, I greater than 0, I minus minus, x of I is equals to x of I plus s. Suppose this is the operation, this is the loop which are getting executed. So this loop in instruction format can be written as this: load f0 0 r1 add f4 f0 f2 store f4 0 r1 and r1 r1 minus 8 and the check r1 r2 loop. So what is happening? So this is basically a loop which does some summation like for all each array element. So if you look at this loop, this is the corresponding like code in assembly. So what happens in this? Basically, first a load operation occurs from the memory. So first we are loading this, then what happens? Like let me just choose a color different. So this is the first statement. So basically first we are loading this array element. Next what we does, we add them. So this happens here. Next what we do, sorry, uh, 1 minute, it is wrong to, we add them. So this is the whole, this is represented by this add statement, f4, f0, f2. Then there is the store. Store is this one. This is the store part, this equal to operation. Then what we do, is this. So basically we do this. We need to reduce the value of R1 at each core. Currently it is 1000. So after like each iteration, it will be minus minus it will be. And last is this check of whether the registers are 0 or not. So basically it is this. This is the equation. So this is the corresponding like address code for this looping statement. So so if you have seen the lectures, so you know here will be one stall because there is one hazard. So this is a read after write hazard. Read after write hazard. So there will be one stall. Between load and add there will be one stall. Between add and store, this is also a hazard, right? This is a write and this is a write, right? So like no, so this is a write and this is a read, and here there will be stall of 2 stalls, and after this there will be one stall because r's value is being checked and here it is saved. So there will be total of 1 2 3 5 6 7 8 9. So it will require 9 cycles to execute one iteration of loop, right? And there will be how many? There will be 4 stalls. So there is 9 cycles. 1 2 3 5, there are 2 stalls, 6 7 8 9. So in total there will be, you will require 4 stalls and 9 cycles. Now we will apply some techniques to reduce the number of stalls. So first technique which we will do is code reordering. So what we will do is we will rewrite the code as this. So we what we did was, here we rewrite the code. So this was the initial code. This was the initial code. We just reordered the code. So like you see that this add instruction R1 R2 has been brought up compared to this. So now some things happen. So now there is no hazard between these two, because F0 is now happening in the as a third cycle. So that like suffices one of the stalls. Now the stall here remains between these two. There will be here two stalls, and there will be another stall between this store and like, no, there will be no more stalls. So these are the only two stalls that will remain if we rearrange the code. So these will be the only two stalls remaining. So now what you see, 1 2 3 4 5 6 7. So now you will require 7 cycles and 2 stalls. So you see, from 9 cycles and 4 stalls, just by reordering the code, it comes down to 7 cycles and 2 stalls. So that is a very big improvement already. So that is a crux of like how CPI can be improved. From previously it was taking 9 cycles and 4 stalls. Now it only takes 7 cycles and 2 stalls. So now one part of our improvement of like CPI we have shown. The next is loop unrolling. So what we will do is, we will, instead of like instead of one of such iterations, we will write 2 iterations and then reorder it. So what will happen is, load f0 0 r1 add for f0 f2 sd f4 0 1 1 ld r1 add f8 f6 f2 st f8 minus 8 r1 add r1 r2 minus 60 dn r1 r2 loop. So now we have unrolled it once. So now it will see that 1 2 3 4 5 6 7 8. So now it takes 8 cycles and there will be no stalls. So if we rearrange this similarly, so there will be no stalls. So that is one of the crux, that by using these two techniques, so once by rearranging and another by loop unrolling, the stalls can be reduced, and also the number of cycles get reduced as a result. So this will on an average take 4. So the question was whether it increases the like number of registers to be used. Yes, it increases the number of registers to be used, but at the same time the cycles that are required decreases. Now that is one of the like, for processors, higher end processors which has more registers, that is a very helpful thing, this loop unrolling. So this is a simple code like that can be that can be used as a example to understand how loop unrolling works and how reordering of the code works to reduce the CPI. If you have any doubt, you can ask regarding this. Okay, so let's go to the next question. So the question is, which of the following is our advantages of vector processor? It gives good speed up when we carry out similar operations on vectors. No loop overhead. The number of instructions get reduced. So what are vector processors? So in a short, vector processors are basically the pipelines plus vector unit. So now what is a vector? Vector, you can consider a vector as a simple array sort of thing. So like if you have an array operation, suppose if you have like done bit of coding of like Python based, like where you have been doing multiplication sort of things. So like you have a matrix multiplication. So writing a code of matrix multiplication by simple looping is a very costly procedure. Like it will take lots of time. But this kind of vector processors help in speeding those things up, because what happens, instead of working on one element at a time, it operates on the whole vector at a time. So that helps in speeding up the operations, because you will be doing the same operations of addition and subtraction on all of them. So using dedicated hardware for those like called vector processors help in speeding up the operations on vectors. So not a like no loop overhead. No loop overhead means like if you are adding to arrays previously, so what you will do, you will just loop over each element and add them. But instead, just if a simple addition of these two vectors are available, so just simple addition, you don't have to loop over it, and it can be done parallelly. So those operation can be done parallelly. So it reduces the number of instructions required. So that is what vector processor means in a in a crux, you can say. So vector processor, you can like simply think about it as a pipeline plus a vector unit. So all of them are correct. If you have any doubt, you can ask regarding this. So like I will repeat once again, like okay. So basically like we have seen the pipeline architecture and all that, which have an execute as an and every execute fetch instructions, decode, write back. So those are operating on a single item. Suppose it may be a floating point or a fixed point integer, those kind of things. But suppose you have been given to add to arrays. So what is the basic technique you will think about? You will think that okay, I will write a loop, and you will add each element and store it in a third element. But is that required if you have a dedicated hardware where this can be done? So that is a kind of thing called vector processor. So it adds basically the two vectors at the same time, because you see it is just basically addition. So why you will loop it? You don't need the loop in that case if you have such a dedicated hardware which can add all the items simultaneously. That's what vector processor does. So as a result, there will be no loop over it, and since all are getting like executed at the same time, so the number of instructions gets reduced. Okay, so I don't know. I don't set the papers. So this is the next question. In a vector processor, suppose the startup time in a vector processor, suppose the art of startup of time of vector multiply operation is 20 cycles. After startup, the initiation rate is 5 initiation rate is 5 clock cycles. The number of cycles required per result for a 128 element vector. So clock cycles required per result for a vector operation of length n is total time divided by vector length. So total time is basically startup time plus n into initiation rate divided by vector length. So basically here it is given. So the startup time of the vector multiply operation is 20 cycles in a vector processor. After the startup, the initiation rate is 5 clock cycles. The number of clock cycles required per result for a 128 element vector. So we have a 128 element vector. What we do is simple multiplication for this purpose. So we need to find out how many clock cycles are required for every such 128 bit vector. So you know this is a streaming kind of thing, like it continues for more than 128 variables, but we need to find out for 128 element vector. So the formula is basically total time required divided by vector length. So vector length in this case is 128. And what is the total time? The first is the startup time. The startup time in this case is 20 clock cycles. It is given. Startup time is 20 clock cycles. Next, it is said that the initiation rate is 5 clock cycles. So there are 5 clock cycles is required for each element, and there are total 128 such elements, and the vector time is 128. So what will be the total time? So this will be actually, if you calculate, it will be 5.156. So basically this is the formula. So you are given a 128, you need to find out number of clock cycles required for per 128 element vector. So what you have given is that what is the initial startup time of the vector multiply operation, like how much time the initially required. Then after startup, what is the initiation rate, that is 5 clock cycles. So the total time required for processing 128 element vector is 5.16 cycles. Startup time, and what startup time is the time initially required, and then there is the initiation rate. So it is given that, see, initiation rate is given as 5 clock cycles. So initiation rate is means for each how many time will be required on an average for each multiplications. So it is 5, and there are how many elements? 128. So 5 into 128 plus 20 divided by 128. So that is the average time that will be required for per 128 element vector. So this is n, and this is the initiation rate. Okay, so let's go to the next question. So which of the following is or true or false for multiple core processor? In asymmetric multiple core processor, all cores are identical. Like which of them false or false? In asymmetric multiple core system, different cores have different functionalities. In a tightly coupled multiprocessor, all processors have access to the common shared memory. So what happens in a like asymmetric multi-core system? We have all cores have different functionality, right? Similarly, for symmetric multi-core system, all core have same functionality. And in a tightly coupled multiprocessor, all processor use a common shared memory to communicate. So in asymmetric multi-core processor, as the name says, all cores have different functionality. They may or may not have the same functionality. But in a symmetric multi-core system, all cores have same functionality. And lastly, in a tightly coupled multiprocessor, all processors have access to a common shared memory. The reason for access to the common shared memory is basically to communicate between the cores. So you need to the core needs to communicate between them, whether some like data are being used. Like suppose one core is writing to one memory address location, and another core is reading from that same memory address locations. So they need to communicate between them to update the final value in the memory location. So that is one of the reasons they need a shared memory so that they can easily communicate among themselves. So that was the last question. So if you have any doubt regarding any question, you can ask. Tell the question number and ask. Uh, week 11. So week 11 assignment question, or the one that was solved here. Yeah. So what you can do is just write the question in the chat. I will check. Yeah, both of you write the question on the chat. I will check. So in this question, basically, we need to find, like, say which of the statements are true or false. So in asymmetric multi-core system, the cores may be same or different. So statement one is false. In is the statement B, in symmetric multi-core system, it is also false. The word symmetric means only that all cores will be similar. And option C, in a tightly coupled multiprocessor, all multiprocessor access to a common shared memory. This is true because that uh, that uh, that common shared memory is required to communicate between the cores. Why? Because suppose one code is writing to one register R1 and another code is using that value register R1 for some other operation. So definitely there has to be a communication between them to check what is the latest value of R1 to be used. So that's it. So option A and B are false. Option C is true. Amulya, this one I will not solve. This one is this week's assignment question. So you need to do it yourself. Uh, uh, Nisha's this question is for the following image speed register using forward and speed register access. So how many stall cycles will be required without any forwarding hardware or speed register access using forwarding hardware or and speed register access? Okay. LW R1 10 R2. LW R1 10 R2. Yeah, I'm checking your question first. Let me solve this one. So the first instruction is load R1 10 R2. So when does this this is basically 10 plus R2, right? So this actually occurs here. Uh, this actually occurs here, right? This execute part, this ALU part occurs here. Then this like loading this, like this value this searching this memory location occurs here, and this loading it to this R1, it happens here, right back, right here. Now what happens here is, if like it is said that we have and we need to add R3 R5 R1 R5. So basically you need to add R1 plus R5. Now if you don't have any data forwarding kind of setup, what happens in data forwarding kind of setup? Data forwarding kind of setup, the memory location is available here, so it can directly use that value, sorry, it is available, suppose here in data forwarding kind of setup, there will be no stall. But if there is forwarding, uh, there will be if there is no forwarding, then there will be stall. So like this was the answer, right? Tearing. But for data forwarding they have given, yeah, man, data forwarding also, like, okay, so I took a very aggressive step here, okay. So like this is like my thought process was that, like, this memory or operation can be done in the second half of this, uh, mm, like in the first half, if the memory operation is done, then in the second half of the execution cycle, the data will be available. So if that kind of aggressive stance is not shown, then in that case we can say that IDEX mem, so data they will be available here, right? So if that is not, that aggressiveness is not mm, like taken, then the data will be available here. So in that case, this is the step where the execution of the addition can take place. So so let's see, LW R1 10 R2 R3 R1 R5. Instruction fetch, instruction decode, main, execute, main, WB. The next will be instruction fetch, instruction decode. Now if data forwarding happens, like what they are saying, that the data will be only available here, so in that case execute will have to be here. and then mem, and then WB. So there will be one stall in that case. And for similarly for no forwarding, in that case it will be two stalls. I mean that's the way of understanding they are going, right? So like what I told previously was sort of correct. Like some books go by that convention that like first half of the cycle only that like that is available, but what they have did in this. So if we take that as a convention, then we can say that it will be one stone. That only the data will be available after the meme operation. Okay, now your is question 9 of last session. Okay, let me check. Yeah, it will be 1.5. Sorry, I thought the CPI was 5. The CPI was 1.5. CPI was 1.5. So that was wrong calculation. So I thought the CPI was 5. Yeah, like it should be. Was it? No, no, no. Like I typed it wrong. So the CPI was 5. So CPI was given as 1.5. That's what I like thought. It was 5. CPI will be 5. Next, week 10, question 9. Assignment. Then copy the assignment question. Right? Copy the assignment question. I don't have the assignment question, so write it in the chat. Yeah, yeah. Take.
In the question, actually, it was asked a bit stuffy. And during the lectures, professor was explaining that we need to get 6 bits. I mean, we need to add 0 after 6 bits in bit stuffing.
What is the question? Can you please just tell me?
Actually, there was given examples, and it was asked for which will be correct after bit stuffing.
After?
There, after bit stuffing,
Bit stuffing for what?
there is a binary code being given, provided binary code.
What was there in like week 10?
Just give me a second. Let me copy the question.
Yeah, yeah. Just copy it. Yeah, if we applied bit stuffing, the output bit will be.
So I have given the answer as B, but the provided solution is D. Actually, initially it was provided perhaps C as the answer. Then I raised the issue, and then other teaching assistant said that actually 5 bits are used. But I said that in the lectures, professor was saying with 6 bits, and if you go to the NPTEL website and check the past assignments uploaded there,
Mm-hmm.
and the solution it also given that you have to go for 6 bits.
Mm-hmm.
So I followed the instructions, and my question was marked as incorrect. So he raised the issue. There was actually two questions, and he raised the issue. So they marked one question correct, and then in this question they marked none of these as the correct answer.
Mm-hmm.
I didn't get As you know, in the lecture, the professor was saying that you have to go after 6 bits when you're adding a zero after 6 bits. So I am not getting that why my answer is wrong, because I opted for B, and you can check that in B after 6 ones there is a zero.
Yeah, this is some beat stuffing, right? I don't remember like in what context this one was there. I mean, like I don't remember. We
In lecture it was said that for output
So can
processing.
you just tell me the which part of the lecture it was asked? I will just check once.
Okay, uh,
I don't
just give
remember
me.
actually which part of the lecture it was there. I don't have the slides with me.
It's in lecture 52, universal serial bus.
Lecture 52.
Yeah,
Okay, okay, okay.
universal serial bus, perhaps in the middle of the lecture.
This is week 10, right?
Sorry,
This is week 10.
week 10. Yeah, week
Okay,
10, lecture 52.
okay, okay. Let me check once.
If you can check the slide, you can easily check that in slide
Yeah, I'm
6.
checking the slide only once. Let me check. This USB one, right? Universal serial bus.
Yeah, yeah, yes and no. Lecture 52.
Lecture 52. So how are data transmitted? So a 0 is inserted whenever a sequence of 6 1 is encountered, right? Okay.
If you check the options, B is correct. I mean, in accordance of what is suggested in the lecture.
1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Yeah, that in that sense. But how is it correct? Then there are another like five. After that, there is no zero given, right? There are two streams of 6 bits, so there will be zero after that also. That is not given, so it will be none of the others.
Why? I mean, I didn't get you. I mean,
There is initially 6 ones, right? Then after few there is also another 6 ones. So after that also there will be 1 0, right?
so it is given. I mean, you can check. Yeah, in another one. I mean, if you go for the option B, after every 6 there is a zero.
Yeah. Uh,
I mean, in the question given, the bit stream is there is only one continuation of six, more than 6 ones.
See, what is written in the slide is a 0 is inserted whenever a sequence of 6 1 6 1 is encountered.
Yeah.
So,
So
so
in the given question, if you go like you start 1000, then after that there is more than 6 ones, so we have to collect 6 ones, then add zero, and then
so my the none of this is correct.
why?
None of you see like first one there is a stream of 7 ones, right? There is a seven ones. So
Okay.
this will be the actual answer. Like I am writing the answer. This will be the actual answer. 0 0. Okay, let me write it in the this tab also.
No, I mean, look, when already there is a zero, we don't need to add zero there.
Why?
We have to break the continuation of more than 6 ones. That's why we add zero. If already there is zero after 6 1, then why we are going to add another zero? It will create the it will create the error.
Is it written anywhere? It is written in the slide. If you check, after a zero is inserted whenever a sequence of six ones in encounter. There are two sequence of six ones here. This is one. This is one. Now satisfied with it?
Can we open the link, please?
Yeah, I'm opening. Yeah, which one? Which one?
The eighth question. Okay, got it. I mean, I think you are saying correctly because in the last option which is given,
Yeah, yeah,
there is
yeah.
easy. There is another question, just one question confusion. Uh, in the write back cache with right allocation, it was given, I mean, it was explained in the lectures. Is
Ha
it
ha ha ha.
possible that,
Just
yeah,
repeat.
yeah, I'm saying that is it possible that we can have write back cache with no right allocation?
Write back cache with no
No right allocation.
right allocation.
Yeah, no right allocation.
So what is the question? Like you say, then I will be able to.
I mean, there were two, types of was. I mean, in the explanation, the professor was explaining this. There are two kinds of right, and I mean,
Slide
there
number
are
you say I will check.
possibilities.
You check the.
Yeah, she was talking about possibilities. So there is one possibility that write back cache with right allocation, and then write through cache with no right allocation. So, I mean, is it possible that we can have a write back cache with no right allocation?
I don't think it is possible.
Yeah, just I mean, I'm just verifying this.
Okay. So if you have any doubt, like I need to end the session now.
Okay.
Okay. Okay. So this was the last lecture. Okay. So
I
best
mean,
of
if you can,
best of luck
just
for your
hold.
exam.
Yeah, I mean, if you can take any,
So
just
see, next week I don't know if they say that.
okay. You can take any day. I mean, before the examination, like 29th of
So
perhaps.
see, I understand that. I'm saying like I they have this was supposed to be my last session. I don't know whether there will be another session or not. That previous used to happen with the professors. I don't know that will happen or not. This link is available. What you can do is uh, just ping me on my mail. I've given you the mail number address. So
Okay.
like so I could have announced that I can take the class, but I'm not sure that I will be present at that time or not. Like next week I may be traveling.
And I'm not, I'm not forcing you to be on the same time of
No, no,
that.
I'm
Whatever.
I'm saying that anytime I know I am saying that that link is available and that link is available at any time. So just ping me on my email and I will help.
Okay. Thank you very much.